Section 4.5 Optimization, page 1. So we've talked about finding max and min values previous sections, but now what's going to happen is we're going to have word problems. So we'll have to create our function, and what generally is going to happen is we'll actually have more than one variable, but we only know how to solve problems with a single variable. So what we can do is rewrite in terms of some constraint and solve for a variable, as you'll see below. So important things to remember. A critical number is the only place that maximum and minimums can occur. And if we have a critical number that comes from the first derivative being 0 and the second derivative evaluated at that exact point is positive, we have a concave up region, which means we have a minimum. Or if the second derivative at that point is negative, then we have a concave down region implying a maximum. Here is an optimization problem we're going to solve. Example 1. A baseball team plays in a stadium that holds 51,000 spectators. When they charge $10 per ticket, they sell an average of 5,000 tickets, so not very many of the seats are taken. When they decrease the price by $2, they sell 10,000 more tickets, not total, but in addition to the amount they already had. Part A, find the linear demand function for price P as a function of attendance X. So here's some key pieces. Linear, we know, is a straight line, and it's a demand function. So the demand, the number of attendees, is based on price. So kind of repeating some of that, for a linear demand function, we need 2 ordered pairs to find a straight line. Since the demand function is based on price, that's the input. It's based on price, which is the output, based on the number of attendees. So we're going to have how many people are attending is going to help us kind of determine the price, the demand. So we're going to create ordered pairs from what we have. The original statement was that they charge $10, they sell 5,000 tickets. So the number of tickets sold is the attendees, and the price per ticket, in our case, is $10. Now, for our second ordered pair, be careful. It says they decrease the price by $2. They're not charging $2. They're charging $2 less, so they're actually charging $8. And remember, it's not selling 10,000 tickets, it's 10,000 more tickets. So the original 5,000 plus 10,000 more is 15 total thousand tickets. So using our y2 minus y1 all over x2 minus x1 formula, we have a negative 1 over 5,000 slope. Using y minus y1 equals m times minus x1 formula, then I can plug in an x1 of 5,000, a y1 of 10, and use my slope. And as I distribute my slope and then add 10 to the other side, to the existing one, I now have a linear demand function for the number of attendees X that determines the price. So now part B says, how should the ticket prices be set to maximize the revenue? So our goal is to maximize revenue. We don't have a revenue function. We need to make a revenue function. The formula for a revenue function is whatever price you have, that's why we needed price to be the output, times how many tickets you're selling. So we're going to take that price function that we had just found and multiply it times X, the quantity of tickets sold, but we don't know what X is, so we're just going to use X in place of X. So really, I'm distributing an X, and now I have a revenue function. Now I have something I can maximize. So we maximize by taking the derivative. So I'm going to have a 2 times that negative 1. I'm going to subtract 1 from the exponent. and 11x becomes 11. We set this equal to 0. So I'm really just going to go ahead and add the 2 over 5,000 x to the other side, and we could have simplified it. I'm going to cross multiply and then divide by 2 to get x. This should be my maximum, but we need to check that it is. So instead of doing a first derivative test, we just said, why not do a second derivative test? Take the derivative of what we have, which really is just negative 2,000 over, negative 2 over 5,000, or in this case, I did decide to simplify it. I need to plug my x value in. Keep in mind, there's nowhere to plug x into because there is no variable, but it doesn't matter. What I care about is I got a negative result. I have something that is concave down, and I know concave down gives me a max. So I have verified that an x value of 27,500 will maximize my revenue, but be careful because how was the question worded? How should the price of the tickets be set? So I know this is how many attendees I want, but we created this formula over here based on X, number of attendees, to tell us the price. So I had to take my X value and plug it in to find out 5.55 or $5.55 is the best price for maximizing revenue.